So, we have been looking at the temporal aspects of interaction of light with matter, which has resulted in qubit manipulations. And this is the specific part of work that has been going on in our particular area of research, and since it relates to all the various different aspects of quantum computing that we have been discussing throughout this course, I thought I will finish it off by looking at the other interaction that also is very important in this particular aspect, which is a spatial interaction concept. So, as in terms with the ion trap condition, where the spatial interaction part was utilized to make sure that the qubits could interact properly and the gates could be associated in this manner, here also we can do the same principle by having a spatial modulation being applied by an optical field. So, in this regard, let me show you how this works. In terms of the spatial control, the basics of optical trapping is being shown here. The trap essentially is of a particle which happens because of the laser beam passing through the particle undergoes bending due to the higher refractive index of the particles in comparison to the environment it is kept in. So, typically a bead which is being trapped in a liquid would be having the higher refractive index and are of typical micron sizes or lower, and having a Gaussian spatial beam would essentially mean that the beam would interact with the bead in such a way so that it is drawn more towards its focus. So, the radiation pressure from the photon flux is utilized in this process of trapping the particle. So, this can be thought in terms of the paraxial Gaussian mode, the spatial mode of the beam, and if a Gaussian beam is not available, in fact, if it is a flat top or a square or a rectangular beam spatially, it will not be possible to trap a particular bead in this particular fashion, because the gradient of the paraxial beam would not be possible to balance the forces. So, for single beam optical trap, paraxial Gaussian beam is essential. Temporarily, however, the laser can be either CW or pulsed. Optical tweezers use light to manipulate microscopic objects. The radiation pressure from a focused laser beam is able to trap small particles. In biological systems, optical tweezers are used to apply piconewton range forces and measure nanometer range displacements in objects ranging in size from 10 nanometers to about 100 millimeters. So, this has a lot of influence in many areas of research, and in this particular case we have utilized the femtosecond lasers for certain benefits. One of the benefit is the simultaneous detection of 2 photon fluorescence and backscatter light, which is possible in this particular case as long as the beads are coated with 2 photon dye. This enables bright field video imaging, and it could be used in both continuous wave or mode lock laser wave operations, either by looking at the scatter or by looking at the 2 photon fluorescence. Since the visibility of the system becomes much better because of the fluorescence, it is possible to have better signal to noise of the trapped particle, and so smaller and smaller particles can be visualized as a result of this particular approach. So, we have managed to show trapping for various range of particles ranging from 4 microns to 100 nanometers quite comfortably. Here is a slide picture which shows 4 and 1 micron particles which are stably trapped with femtosecond 800 nanometer lasers. The principle of trapping works easily with the 2 photon fluorescence, because the fluorescence comes from only the focal point where the intensity is high enough to produce the 2 photon fluorescence signal. In every other place the photon fluorescence signal is not possible to be generated, and so the focal plane wherein the particle get trapped is easily detected. So, spatial trapping with the help of optical pulses can be utilized towards trapping smaller and smaller particles. So, we have gone to particle sizes which are either in the range of wavelength of the light used or even smaller than that. Under those conditions, the force depends on polarizability, and for example, latex nanoparticles are hard to trap. High peak power of an ultra short laser pulse helps. However, the repetition rate is also critical. If the pulses come after a very long time, then the stable trapping time will not be possible to be maintained. So, here is a cartoon of how this particle trapping works. The particle is basically put into a potential created by the optical field, under which the particle gets trapped. When the pulse goes away, particle experiences no gradient force. However, when the pulse is not present, the particle experiences no gradient force. However, the Brownian motions or the fluctuations within the beam waist continue as long as the next pulse comes before the Brownian motion takes the particle away from the trapping zone, the particle remains trapped. And so, that is the reason of the repetition rate of the laser to be sufficiently high to make sure that the particle remains trapped. So, here is a cartoon of how a microscope objective essentially traps a particle in its force field, and mostly this force field is thought to be modeled as a harmonic potential, wherein the particle is sitting at the close to the minima of the harmonic potential. That is how the model is being developed. And what we have found is that it is also possible to have multiple particles come together, because as the particle size goes lower, the zone in which the particle trapping can happen can be large enough to accommodate more than one particle, and that would enable multiple particle trapping. So, for instance, with a 100 nanometer lated bead particle with 800 nanometer wavelength laser pulses, we are under the condition where the wavelength of light is greater than the diameter of the particle being looked at. So, it is in some sense better than the diffraction limited condition. This can be observed through 2 photon much easily once the system is calibrated by using backscattering data of 4 and 1 micron. The particle aggregation can also be tagged through the extremely sensitive technique. And so, here is the case where we can see a second particle coming into the trapping zone and seeing a 2 particle trap. Simultaneous coupling pulse shows that this efficient and sensitive ultrafast optical tweezers is possible to let us reach our goal towards spatial temporal control and spectroscopy. So, that is one of the interesting parts of having a trap which can enable the motion of particles. So, this is in some sense analogous to the condition which we have discussed earlier, where we have atoms in lattice. So, we could imagine if we could produce traps where we could put the qubit like objects to be coupled by using optical particles, by using optics, such that they could then be made to interact and things. However, at this point of time, atom trapping is not really out of reach in terms of the conditions that we are using, but the same principle works for the atom lattice that we have used before or discussed before in our regular lectures for quantum computing here. So, the backscattering technique can help us set the problem, and then using the fluorescence coming from the 2-photon fluorescence coming from the trapped particle, if the calibration is made right, it can help us go down to look at smaller and smaller particles. So, that way quantum dots of 16 nanometer particles have also been trapped. We have also seen multiple trapping, as we discussed before, and so these are interesting developments which have been utilized. One of the things which we notice while this particular work has been developed is the fact that the fluorescence, the 2-photon fluorescence coming from these trapped particles also show a decay property which is not quite expected, and these decay occur not for the very small particles. For example, the 100 nanometer particle does not show any decay even when they aggregate. However, the larger particles, for example 1 micron or 4 micron, they show decay, and once the smaller particles, say 500 nanometer particle, individually even if they do not show any decay, when they start aggregating they start showing decay, essentially indicating the fact that as the size of the particle getting trapped is increasing to a size which is beyond certain limit, then there is a decay feature which appears in at least the fluorescence signal that we are using. So, when we looked at this particular process, we had to understand as to how this was happening. We did not see any of this kind of a decay feature to appear in the backscattering signal for these kinds of microspheres. However, the decay was always evident from the fluorescence signals. So, one of the ways that we understood this problem was to realize that these particles are essentially undergoing some sort of energy transfer when they reach a condition where part of the particle is not able to see all the light, because when the particle size is smaller, then the particle is always immersed in the photon flux. However, as the particle size gets larger, like 1 micron, 2 micron, 4 micron, because our laser wavelength is 800 nanometer, all of these particles are larger than the zone in which the light is getting focused in terms of diffraction limited conditions, and as a result of that these larger particles are not getting illuminated all through. That is one of the reasons why this can undergo energy transfer within the illuminated versus the non-illuminated zone, and that can lead to a decay of the fluorescence that has been observed. And we did a very simple model to ratify our conjecture, and it was interesting to note that even with the very simple approach of assuming a cone of the beam coming in and a circle to just represent the size of the bead, but just taking the ratio of the illuminated versus the non-illuminated part, a simple model could be developed where the decay was quite well correlating to the size of the particle that was being used. So, we were able to use this idea to easily understand how the size of the bead was affecting the way the trapping was going on. Once we detected that, it also brought up an interesting concept that as the particle size increased, which is what we had noticed earlier, that for a 500 nanometer particle which is embedded within the 800 nanometer wavelength light in the focal spot, as the particle size is increasing because of aggregation, we also see the same effect, that there is a decay in the multiple particles fluorescence, and this is our observation in terms of linear polarization of light first used, no decay in the TPF signal up to 2 particle trapping, TPF intensity decay in 3 particles with some time scale and 4 particle with another time scale of decay. Up to 2 particles, the whole microsphere system stays within the focal region, so there is no decay seen. This indicates that the 2 particles position along the z axis and not along the radial axis, and that has been shown earlier with some theoretical studies. So, this is one of the interesting experimental proofs of the fact that the particle essentially is aligned in the direction of the laser beam for the linearly polarized light. However, when circularly polarized light is used for trapping, there is a decay which is again evident for even the 2 particle case, and that is possible because for the circularly polarized light, the dimer undergoes tumbling motion, and as such it could be either aligned along the axis or along the equator. So, in circularly polarized beam, due to rotation of the cluster, some area of the cluster remains outside the illuminated zone, and so the decay can happen. Now, the experimental spikes that are often seen in these kinds of trapping experiments are due to the bias diffusion of large size clusters, which are experimental difficulties which happen sometimes, and as they go through the focal region, these kinds of spurious features may come, but these can be minimized as the concentration of the system is reduced. So, the overall story correlated very well to the theoretical prediction which was earlier done based on the interaction of the laser with dipolar particle assumptions, and our experiment essentially proves the fact that when we do have this kind of a scenario where particles are getting trapped, and if they lose their symmetry because they are going to become a dimer, then they are going to align along the direction of propagation of the laser rather than in perpendicular to the direction of propagation of laser. So, we found several different aspects of application of this particular spatio-temporal control of systems that we have developed until now. We have been also looking at how interaction in time can change the property of the system that we discussed in the previous studies, and one of the ways of development of a quantum computer in this particular aspect will definitely be involving an interaction with both time and space, as we have been showing here. So, with this I would like to actually conclude our understanding and study of quantum computation, implementation and other aspects that we have been dealing with in this course. I have tried my best in explaining all the different aspects which have come into this field over the years of development. Initially, the development of this field has been extremely rapid with a lot of input, and then there was a period where a lot of questions were raised and a lot of understanding needed to be developed. So, the initial years, which were also fueled by the fact that Feynman realized that quantum systems need quantum computers to have the best results, brought in the entire principle of interest in this area of quantum computing. For a while, there was a lot of development, and because universality was established by Deutsch, then after there was a period where a lot of questions were raised on the viability and the error aspects of the problem, which were uh, built on, and the first important development came when Shor was able to show the algorithm which works exponentially in speed, which is what is the expectation of this um, realization of the fact of quantum computing in reality. And thereafter, Grover's algorithm and many other processes and many other developments has happened. Many important people have, many important developments have made contributions to this field, which are very critical, and it is still a very growing field. So, many aspects that we have discussed here are still being explored, and many of it is perhaps going to change over the next few years as we realize much better ways of dealing with these kinds of ideas. So, with that, I would expect that this particular kind of course would need to get upgraded in some years, because a lot more new information will come in and a lot more interesting results will be there to be presented in such a evolving, developing course. But there is a lot of interest, and I hope you all enjoyed the course, and I look forward to having interacting with you in the years to come in the future. Thank you.